When working with real, observed, or experimental data, it's very possible that we're going to actually have more equations than we have unknowns, in which case we're going to have an overdetermined system of equations. So an overdetermined system is when we have more linearly independent equations than we have unknowns. Thinking about that A matrix we've been working with, it's an A matrix where we have more rows than we have columns. It is not square, and we are not going to be able to find a unique solution to this, because as we saw before, one of the requirements to have a unique solution is that A is a square matrix. Now sometimes we can have a unique solution if we were to have repeated equations in our linear system, but for most of the ones we're going to see here, it is not going to be true that we will have a unique solution to the set of equations that we have. So if we can't find a unique solution that satisfies the equations, then what are we trying to do? Well, we want to find the coefficients that provide the best fit for the data that we've observed or the data that we've collected. And this is very similar to what we've been doing before with the fitting toolbox, the curve fitting toolbox. We were trying to find, in those cases, what line or curve or model best described the data that we had. Here we're going to be able to do it for linear systems, and in more advanced techniques we can use nonlinear systems also, but we're going to stick here with linear systems. So the idea is going to be the same. We want the line, or we'll see plane, that best passes through the data that we've collected. And what we're going to see that's new here compared to using the curve fitting is we can look at data that has multiple independent measures and one dependent variable. But we can also look at systems with one independent variable and one dependent variable, really the same way we were using the curve fitting toolbox before. If we're collecting data, it's not really a concern to have to rewrite any of the equations, but the general idea here is that our A matrix is going to contain all of our independent variables that we've measured. And then the right-hand side, that B vector, is going to contain all of the observables or the dependent variables that we're measuring. So for example, we might be interested in how age and weight correlate to someone's cholesterol level. So the A matrix, the first column of the A matrix, might contain weights of people that we've measured. The second column might contain the ages of people that we've measured. And then that B would be the cholesterol that we've measured. And the basic idea here is if we only have measured someone's age and weight, we want to have our best guess as to what that person's cholesterol level is going to be. So we're going to create an equation where we take our independent measures, multiply them by coefficients, add them together, and we get our best estimate as to what that dependent variable is. So we're still looking for this x vector, but x is now coefficients that we're multiplying our observed, our measured data by. And to solve for the best coefficients to use that best matches our data, we're again using that backslash operator here, but now again A is not a square matrix, and we have that column vector B that we're going to be using.